So this is joint work with my collaborators, Ian Yan, Jie Chen, and Rui Yan from the IBM Research, UT Austin, and Baidu. So I will first, this is outline about this talk. So in this talk, I will first introduce Kernel method and why we want to study Kernel method and what's the current state-of-art method for the Kernel approximation techniques. And the second part, we will go to the random billing. This is a feature we try to revisit in this paper, and we show the power of this feature. And then we talk about the advantage of random billing in terms of two different perspectives. The first one is a theoretical result, is random billing shows a faster convergence compared to the other random features. And the second contribution is that we propose a new algorithm called sparse random billing. Basically, we combine random billing with L1 realization, and we'll show that because of the spatial structure of the random billing feature matrix, that we can achieve a very strong parallel performance. And finally, I will show extensive experiment to demonstrate our claims, and I will conclude my talk and give the future works. Okay, so Kernel method is one of the standard methods for the nonlinear learning. So there are many applications, regression, classification, feature extraction, clustering, dimensionality reduction. So, but one of the bottlenecks for the Kernel method is that it's very hard to scale to the large scale data set because quadratic complexity in the number of the samples. So there are many techniques try to scale up the Kernel machine. So one of the most popular method probably is Nystrom method, and it has many variants. So basically, try to select a set of the landmark data point and to construct a low-rank approximation in the perspective of the numerical niche algebra. So another set of the family is called the random feature approximation. So basically, this random feature approximation, you try to directly approximate the Kernel function itself, and then to build a low-rank approximation for the Kernel matrix. And they have three different methods. Random Fourier, random billing are two methods that are proposed in the same paper, in the Rahani 2007 Lips paper. And later, random Fourier gets very popular, but the random billing, no one take a look at that. In this paper, we'll show that random billing actually is a very powerful technique and can be much more converging much faster than the random Fourier. And the last one is fast fold. It's kind of a recent proposed technique. Basically, it's close to the random Fourier, but because it leverages a different basis function called a Hadamard function, so that it can admit more efficient storage and computation. And they also have other independent Kernel approximations. For example, the independent block approximation basically is a block diagonal approximation for the Kernel matrix, and the mecha and compositional Kernel, and many techniques. Okay, so but all this technique, it try to reduce the computation and the memory from the quadratic complexity to the linear complexity. In terms of that, if the R here is the rank, so if R is quite small and compared to the N is the number of data point, then we call it a linear algorithm. However, in the practice, when in terms of the very large scale data set, and if we want to achieve the very comparable performance compared to the exact Kernel method, then typically we observe that it's quite a very slow convergence. Typically, the number of the R is linearly proportional to the N. That means that you lose your advantages. So in this paper, we try to discuss the random billing feature. And so first, let's look at the Mercer theory, because in this theory, it guarantees that any positive definite kernel permits feature map decomposition. However, this composition is not unique. You can find a different feature map, try to construct the same Kernel function. For example, you can use random Fourier, random billing, and fast fold to construct the same Laplacian Kernel function. Therefore, we want to ask the following question. Does some of the feature map lead to fast convergence than the others in terms of approximation? Because this is a very important question we need to want to answer. So First of all, let's look at what's the random binning feature and why we say that the random binning feature is kind of an interesting, very powerful technique. So basically, random binning feature also have a decomposition that try to approximate this Kernel function. That is the inner product between the featured matrix. And here, the random binning is try to partition the data space with a randomly shift grid with arbitrary resolution. So if the one data point located in one bin, then we think that the feature matrix applying on the data point will be the zero. There will be a value 1. Otherwise, it will be 0. So and also as shown in this, so let's take a look at the right figure. Okay, it's much easier to understand this technique. So basically, it's a very simple example here. Here we only consider a data space with a 2 dimension. So we can partition this data space. So the delta 1, delta 2 are the parameter that we draw from the distribution that corresponding to the kernel function. And the mu1, mu2 is value is drawn from the uniform distribution. Okay, so that's how we generate this randomized grid. Okay, so then any data point, you will see that it will located in one bin, right? So once this data point located in one bin, then it will generate a feature there. And they may have, if this bin is very large, then the many data points may locate in one bin. And that means that this data point share the same feature. And if the like say in this figure, x2 located in different bin, so then we find the different feature. And so we can see that the random binning is kind of a technique that even though we use only one grid, however, we can find many features. So this is very different from the other random feature method that only one time you only generate one feature. However, random binning is not. It will generate many. That is kind of intuitively speaking that why random binning have a very more impressive power to rapidly transform the low dimension data space to the high dimension feature space. Okay, so in this paper, we prove that if we consider the random, so okay, let's go back a little bit. So if we go back to the original paper, in the Rohani paper that proposed the random Fourier and random binning, the convergence bound for this both feature actually is from the Monte Carlo analysis. They have a very similar bound. So but it's very hard to explain why in practice why random binning have a much faster convergence than random Fourier. So right now we are trying to consider random binning in a different way from the optimization perspective as the block coordinate descent method on the infinite dimensional problem. Okay, so this is our objective function. So the main result we have here is that if we draw a random grid, and then the solution W we obtained from the random binning will be in terms of the objective function compared to the exact solution from Kernel method have this bound. And this bound here, the R is the number of grid as we mentioned in the theory. And the couple here is the expected number of the non-empty bin created by the random grid. Okay. So how to interpret this theory? So basically you can think about that. So we also have another paper try to analyze the random Fourier features. If we use that same analysis framework, then even in these cases, the random binning still have a couple times speedup compared to the random binning, random Fourier feature. And if we compare to the original analysis from the Monte Carlo analysis, then our bound is much more tight, and explain why the random binning have a much faster convergence because it have two parameters to control the final result. Okay, one of the extreme cases you can think about that if we have a random grid have a very small resolution, that means that each bin is very small, and then each data point will located in different bin, and then in this case basically use a grid to memorize all your data points. Therefore, the training loss will be 0. Okay, so now let's discuss. So you can see that because each data point will only locate in one bin. Therefore, when you generate many features, you will see that the final feature matrix will be a very sparse matrix, as I show here. We want to explore the structure of this random binning. So we combine random binning with the L1 regularizar, try to generate a sparse random feature that will admit most sparse predictor vectors that have a better prediction time. And so in order to solve this problem, the coordinate descent method is the one with the step-out method. And it's well known that, so here, if you want to parallelize the coordinate descent, you need additional assumption of the guaranteed to achieve the guaranteed speed up. So in this, in 2015, this paper it shows that if in your objective function, if it's R is your regularizer, if it's separable, and if your loss function is partially separable, means that the FW here only involve omega number of the coordinate lengths, and then you can achieve the guaranteed speed up, the d by the omega parallel speed up. I think the previous talk, the speaker is already discussed how the parallel coordinate descent. So I think here is have a very similar idea, but we didn't do the in the cloud. Okay, so in the random binning setting, we can see that the omega here is just R. Therefore, we can have the expected speed up that d by R is kappa. So we can have a guaranteed speed up with kappa. So if we, so the left figure show here that is example, what is a feature matrix that a random binning generated looks like. Okay, so you can see that even though we only use 10 grid, but we already generate a feature matrix that have a 395. This is a very large sparse matrix. So in our experiment with a million samples, we can generate even billion size of the feature matrix. Therefore, it's very sparse because it's very sparse. So you can when you update that, the coordinate descent will not have a very large complicated. So you can have use randomized coordinate descent to achieve the quadratic descent speed up. And so how to control this kappa is the key, right? So as I mentioned before, kappa is drawn from the distribution corresponding to the kernel. Okay, so as shown in this right figure, if you have a large draw larger values there, then you will have a larger resolution. Then you will have a large grid. Then the more data point will located in one bin. Then you will generate a few feature, right? So kappa then is small. If you have a smaller bin, that means you have a very compact grid, then you will have a larger kappa. In our setting, we would like to have a large kappa because that's the power that random binning can express that other random feature cannot express. Okay, so now let's look at the experiment and to show. To demonstrate our claims of these two advantages of random binning feature. Okay, so we compare random binning with the light-strong method, with the Random Fourier method, with the independent block approximation, and also use that Kernel method. Okay, so here we pick the data set from the different tasks. So first two is a regression task, and then in the middle is a binary classification task, and the final three is a multi-class classification task. Okay, so and in terms of the feature, people may care about that, so we choose a very different one. So from the small number to the large number. The largest training set is a SUSI, is 4 million and 1 million in training and testing. Okay, so first thing we want to study is that we want to study the effect of the sigma and R on the random binning feature. Okay, so the R here, as I mentioned, is a number of the grid you want to draw, and the sigma here actually is related to the kappa. Okay, so we want to study these two parameters separately. So first we look at let's look at the left top figure that we first keep R fixed and to increase the sigma. That's what means that I will change the kappa. Okay, so we can see that the testing accuracy and the training accuracy. Actually, it's error because it's a regression. So it's decreased at the very beginning. That makes sense. And the black line there is from Kernel, is a exact solution from Kernel method. And when you certain point, the training will continue decrease because the random binning have a very strong overfitting skill. And but once you cross certain point, the test point will go up. That makes sense. This is so the second figure shows that is that. So because R is only used to control the memory consumption and also the computational cost. And here, when you increase kappa, it doesn't increase any complexity. But in practice, you may have a large constant. So you want to see that if this constant is large, that make random binning less competitive. So that's why we want to plot this figure. The black box there is to show that what's the best performance. So you can see that when you achieve the best performance, your computational time is still very close to the lowest point. So that's very good. So in the right figure, we show that here we try to fix sigma and then to increase the number R. So this is very straightforward. So typically, people understand very well. When we increase the number of R, means that we will build a better low-rank approximation, and then therefore we can have a better performance. So the second, in the bottom three figure corresponding from the multi-class classification result. So it's a very similar trend. You can see that. So I only want to make a comment to. I want to make two comments. First of all, the sigma here is only related to the random binning. Okay, if you use the random Fourier, there's no such a parameter that you can tune that to get this kind of figure. Okay, this is a special thing about random binning. The second thing that if you look at the right bottom figure, so you can see that when we fix the sigma, when we increase R, even though when the training data set is very strong overfitting, but you can see that the testing accuracy is still increased. So that means that when your hypothesis is not saturated, the overfitting is not a bad thing. Sometimes overfitting is a good thing to increase your performance. So okay, so now let's compare all these methods, the popular method, the step R method we want to compare. In the first task is the regression task. So the left top figure is to show that when we increase the number of the R, so R here in terms of the different method is have a different meaning, okay? But it's a fair comparison because R here is to control the memory and computation you are going to use for your method. And here we see that the random binning can converge much faster than other methods. And if you look at the right, the top right, you can see that the computational cost is comparable. So that's good because we don't want to see a method that have a faster convergence but is computed very slowly. And if we look at the bottom figure, here I show that if I want to achieve the same testing accuracy, how many computation, how many memory do I need? So you can see that the first figure, in terms of training time, the random binning is at least 100 times faster. In terms of memory, it's the same thing. So this is recursion case. Okay. So now let's go to binary classification cases. So here you can see that in the left bottom, left top figure, the random binning converges very fast to the very good performance at the very beginning. And then the other method get improved when you increase of R, but still is much worse than the random binning. And look at the right figure, the computational cost is still very comparable. That's the thing we want to see. And in terms of to achieve the same testing accuracy, how many training time and memory do we need? Now you can see that it's 1,000 times faster than other random feature and other approximation. And that's the same thing you can see that in terms of the memory consumption. So here finally is a multi-class classification. Okay, so we can see the same trend we observed before. The random binning converges much faster, and computation is very comparable, and the training time here and the memory consumption in terms of to achieve the same testing accuracy is about 100 and 100 times better. Okay, so finally let's demonstrate the second, the strong benefit of the random binning is parallel performance when we talk about sparse random binning and sparse random Fourier. So as I mentioned before, because of random binning can generate a very large sparse feature matrix, so it's have a very good potential to achieve the strong parallel performance. There's here is not like a previous talk. It has some trick. There's no trick here. You just apply a very, OpenMP shared memory coordinate descent method, then you can achieve this speed up. And we can see that random binning can achieve a very decent speed up, but the random Fourier have no speed up at all. That's because that the random Fourier will generate a very dense matrix. That means that the coordinates is not separable. Okay, so let's conclude this talk. So we reviewed the random binning feature in this work, and this is, we think, is overlooked by the very powerful technique that often have 1 to 3 order magnitude faster than other features. And by interpreting the random binning as a randomized block coordinate descent method in the infinite dimension space, the random binning can achieve a much better convergence rate. And in order to explore the sparse structure of the random binning, we can utilize the randomized coordinate descent to achieve the guaranteed speed up proportionally to the kappa. And finally, I would hope that I have convinced you guys that random binning is a very useful technique and can be used in many large-scale machine learning techniques. One of the future work I'm going to do is that I'm going to apply this to a speech correlation, because in our previous work we have shown that combine the random Fourier with some special technique, you can achieve a very comparable performance compared to the deep learning result. And the random binning now, I think, is very promising towards this direction too. Okay, thank you.
Thank you. Questions?
Thank you for your talk. So this random binning method is a kind of incremental learning, or given more training data, or you have to do it again? I mean, if you have more data.
So the random binning actually is not related to the data itself. So if you look at the experiment we show there, I intentionally to list this table. You can see that data set you have small data set, have larger data set. It's not related to that. So the only thing you have to do is that you have to tune the parameter kappa and the R, so that you want to achieve the best performance that satisfy your application.
So you mean it is independent of the data, the training data? It will relate, but it will not rely on the data to achieve the good performance. Okay, thank you.
One more? Okay, I have one question. So with small r, your algorithm achieves the highest improvement. So can you give us some intuitions why?
Here, right?
Yeah.
Okay, so yeah, basically it discusses the left top figure. Okay, so even though we have a very small r, but still we have a very good performance there. Yeah. The reason is that, so for random binning, the parameter is not only related to r, it's also related to kappa. And kappa is how you tune the sigma. Basically, it's bandwidth of the kernel. If you choose a small bandwidth, means that you will generate a grid with a very small bin. That means that you generate a more feature that gives you more power to express your data, to rapidly transform the low dimension to the very high dimension.
Okay. Okay. Let's second speaker again.